Testing, can you hear me? Hello? Testing, can you hear me? Testing again, can you hear me? Okay, I'm going to be studying discrete math. This is probably going to be the finite stream on the book I'm reading. And it's about the introduction to number theory. Let me just change to full screen. So, in this book, I've read through the chapters, and introduction is the last chapter remaining. And yeah, I will read a separate book on number theory as well. We have used natural numbers to solve problems. This was the right set of numbers to work with in discrete mathematics because we have always dealt with a whole number of things. The natural numbers have been a tool. Let's take a moment now to inspect that tool. What mathematical discoveries can we make about the natural numbers themselves? This is the main goal of number theory, a huge, ancient, complex, and above all, a beautiful branch of mathematics. Historically, number theory was known as the queen of mathematics and was very much a branch of pure mathematics, studied for its own sake instead as a means of understanding real-world applications. This has changed in recent years, however, as applications of number theory has been unearthed. Probably the most well-known example of this is RSA cryptography. What sorts of questions belong to the realm of number theory? Here is a motivating example. Which amount of postage can be made exactly using just 5 cent and 8 cent stamps? You're able to prove that any amount greater than 27 cents could be made. You might wonder what would happen if we changed the denomination of the stamps. What if we instead had 4 and 9 cent stamps? Would there be some amount after which all the stamps would be possible? Well, again, we could replace two 4 cent stamps with a 9 cent stamp, or three 9 cent stamps with seven 4 cent stamps. In each case, we can create one more cent of postage. Using this as the inductive case would allow us to prove that any amount of postage greater than 23 cents can be made. Where we had 2 cent and 4 cent stamps, here it looks less promising. If we take some number of 2 cent stamps and some number of 4 cent stamps, what can we say about the total? Okay, let's just skip this example. It is easy to add and multiply natural numbers. If we extend our focus to all integers and then subtraction is also easy. We need the negative number so we can subtract any number from any other number, even larger from smaller. Division is the first operation that presents a challenge. If we want to extend our set of numbers so that any division would be possible, maybe excluding 0, we would need to look at rational numbers, the set of all numbers that can be written as fractions. This would be going too far, so we will refuse this option. In fact, it is a good thing that not every number can be divided by other numbers. This helps us understand the structure of natural numbers and opens the door to many interesting questions and applications. If given numbers a and b, it is possible that a divided b gives a whole number. In this case, we say that b divides a. In symbols, we write b divides a. If this holds, then b is a divisor or factor of a. A is a multiple of b. In other words, if b divides a, then a is equal to bk for some integer k. Given integers m and k, we say m divides k and write m divides k, uh, provided n divided by m is an integer. Thus, the following assertions mean the same thing. M divides n is equal to mk, m is a factor of n is a multiple of m. Notice that m divides n is a statement, is either true or false. On the other hand, n divide m or n divided by m is some number. If we want to claim that n divided by m is not an integer, so m does not divide n, then we can write m does not divide n. Decide whether each of the statement below are true or false. True, false. 0 divides 5. Yeah, 0 can divide 5 into 0 pieces. 4 can divide 20 into 5 pieces. 5 divides 0. 0 divides 5. 5 divides 0. Well, this is an error, right? We are asking if 5 can cut nothing. If we can cut nothing into 5 pieces. 7 divides 7, this is true. 1 divides 37, this is true. Minus 3 divides 12, this is true. 8 divides 12. 1642 divides 136299. Okay, I don't know. True, false. 5. Okay, this is true, this is false. 5 divided by 0 is not defined, let alone an integer. So 0 divides 5. So we are asking to cut 5 into 0 pieces. Okay, the fourth one is true. In fact, x divides 0 is true for all x. This is because 0 is a multiple of every number. 0 times x is 0 is equal to x times 0. This is true, 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 false, and false. Last example raises a question. How might one decide whether m divides n? Of course, if you had a trusted calculator, you could ask for the value of n divided by m. If it spits out anything other than an integer, you know m does not divide n. This seems a little like cheating though. While we don't really know how to divide, we do know how to multiply. We might try multiplying m by larger and larger numbers until we get close to n. How close? Well, we want to be sure that if we multiply m by the next larger integer, we go over n. For example, let's try to divide whether 1642 divides 136299. Start by finding multiples of 1642. All right. All of these are well less than 136299. I suppose we can jump ahead a bit. Then 85. So we need to look somewhere between 80 and 85. 80, 85, okay. And then 83 is this. 286. But if we add 1000 to this, like times 84 will go overboard, right? Is this the best we can do? How far are we from our desired 136299? If we subtract, we get 13. So we know we cannot go up to 84. That will be a little too much. That will be too much. In other words, we have found that 136299 is equal to 83 times 1642 plus 13. Since 13 is less than 1642, we can now safely say that 1642 does not divide 163299. It turns out that the process we went through above can be repeated for any number or any pair of numbers. We can always write the number a as some multiple of the number b plus some remainder. We know this because we know about division with remainder from elementary school. This is just a way of saying it using multiplication due to the procedural nature that can be used to find the remainder. This fact is usually called division algorithm. Given any two integers a and b, we can always find an integer q such that a is equal to qb plus r, where r is an integer satisfying r is from 0 to b. The idea is that we can always take a large enough multiple of b so that the remainder r is as small as possible. We do allow the possibility of r is equal to 0, in which case we have b divides a. The division algorithm tells us that there are only b possible remainders when dividing by b. If we fix this divisor, we can group integers by the remainder. Each group is called the remainder class modulo b, or sometimes residue class. Describe the remainder class as modulo b. So remainder classes are all the integers that gets divided by b, right? So basically just the multiples of b. We want to classify numbers by what the remainder would be when divided by 5. From the division algorithm, we know there will be exactly 5 remainder classes because there are only 5 choices for what r could be. First, consider r is equal to 0. Here we are looking for all numbers divisible by 5. Since a is equal to 5q plus 0, in other words, the multiples of 5, we get the infinite set. Next, consider r is equal to 1, with which integers when divided by 5 have remainder 1. Well, certainly 1 does, so does 6 and 11. 6, 11, 16, 21, 1 minus 4 minus 9, 14. There are 3 more to go. The remainder classes for 2, 3, and 5 are respectively this and this. So remainder classes modulo 5. This is for r is 0. This is for r is 1. When r is 2, when r is 3, when r is 4. Note that in the example above, every integer is exactly in one remainder class. The technical way to say this is that remainder classes modulo b form a partition of the integers. It is possible to develop a mathematical theory of partitions, prove statements about all partitions in general, and then apply those observations to our cases here. The most important fact about partitions is that it is possible to define an equivalence relation from a partition. This is a relationship between pairs of numbers which acts like in all the important ways like the equals relationship. Again, there is a mathematical theory of equivalence relation which applies in many more instances than the one we look at here. All fun technical language aside, the idea is really simple. If two numbers belong to the same remainder class, then in some way they are the same. That is, they are the same up to the division by b. In the case where b is equal to 5 above, the numbers 8 and 23, while not the same number, are the same when it comes to dividing by 5, because both have remainder 3. It matters what the divisor are. 8 and 23 are the same up to division by 5, but not up to division by 7, since 8 has a remainder of 1 when divided by 7, while 23 has a remainder of 2. With all this in mind, let's introduce some notation. I want to say that 8 and 23 are basically the same, even though they are not equal. It would be wrong to say 8 is equal to 23. Instead, we write 8 is equivalent. How do you pronounce this? Congruent. 8 is congruent to 23. But this is not always true. It works if we are thinking of division by 5. So we donate that somehow. What we will actually write is 8 is congruent 23 modulo 5. And it's not congruent 23 modulo 7. We say A is congruent to B modulo N and write A is congruent to B modulo N provided A and B have the same remainder when divided by N. In other words, provided A and B belong to the same remainder class modulo N. Many books define congruence modulo N slightly differently. They say that A congruence B modulo N if and only if N divides A minus B. In other words, two numbers are congruent modulo M if their difference is a multiple of N. So which definition is correct? It turns out it doesn't matter, they're equivalent. To see why, consider two numbers A and B that are current modulo N, then A and B have the same remainder when divided by N. We have A is equal to Q1N plus R, B is equal to Q2N plus R. Here are two R's, here the two R's really the same. Consider what we get when we take the difference of A and B. A minus B is this minus this, which is Q1 minus Q2N. So A minus B is a multiple of N or equality. N is divides A minus B. Consider what happens if we divide each term by N. Dividing A by N will leave some remainder, as well dividing B by N. However, dividing Kn by N will leave zero remainder. So the remainders on the left hand side must cancel out. That is, the remainders must be same. Thus, we have A is congruent B modulo N if and only if N divides A minus B. It will also be useful to switch back and forth between congruences and regular equations. The above fact helps us with this. We know that uh, A modulo B, is congruent to B modulo M if and only if N divides A minus B, if and only if A minus B is equal to Kn for some integer K. Rearranging that equation, we get A is equal to B plus Kn. In other words, if A and B are congruent modulo N, then A is B more than some multiple of N. This conforms with our earlier observation that all numbers in a particular remaining class are the same amount larger than the multiples of N. So this, if and only this. We said earlier that congruence modulo N behaves in many important ways, the same way equality does. Specifically, we could prove that congruence modulo N is an equivalence relation, which would require checking the following three facts. A, given any integer, the following hold. A is congruent to itself. If A congruent B, then B congruent A congruent B, and B congruent C, then A congruent C. Congruence modulo is reflexive, symmetric, and transitive, and so is an equivalence relation. We should take a minute to convince ourselves that each of the properties above actually holds for congruence. Try explaining each using both the remainder and divisibility definitions. This is trivial. If A congruence B, then B congruence A. I mean, we can put K into the other side, and then that will prove the point. A congruence B, which means this is true. B congruence C. You have to replace B by C plus Qn. Okay, C plus Qn plus Kn. That would mean C plus, wait, what I'm saying is A modulus B mod N means A is equal to B plus K and B modulus C mod N B is equal to C plus Q N, and then A C mod n. Like if we do these two together, we get these two together, we get A is equal to C plus Qn plus Kn. This is B, which is equal to C plus, which is equal to C plus, right? And then we got A, C, some integer H, N. Next, consider how congruence behaves when doing basic arithmetic. You already know that if you subtract two congruent numbers, the result will be congruent to 0. What if we add something congruent to 1 to something congruent to 2? Will we get something congruent to 3? Suppose this A congruent B and C congruent D, the following will hold. This, and this. Okay, we can prove that simply. So let mod n and so uh yep. So A plus B, sorry, A plus C is equal to B plus Kn plus D plus Qn, B plus D, and then I will group K and Q together. K and Q n plus H n. Therefore, and then a similar argument for minus, and then we have AC AC BD BD plus BQN plus KDN plus KQN square. Notice we can extract the n out. So BQ plus KD plus KQN multiplied with n, and then BD, I will group this as H, and therefore I should write some other letter. J. BD mod n. Find the remainder of 3941 divided by 9. Should I just use a calculator? What is 3941 divided by 9? I think what they want us to do 6.2.3. They want us to do something like this, right? You could do long division, but there is another way. We want to find x such that x modulo 3491. You know 3491 is this. Of course, 90 modulo 0. You can replace 90 in the sum with 0. Yeah, but the thing is, just because we prove this doesn't mean we prove the other way around, right? That's a different proof. Hold on. So what they're doing is 3,400 plus 90 plus 1. They're doing this. Zero mod and 3,000 plus 400 plus 1. What's the proof of doing this? Oh, I think maybe we can reason backwards. But the thing is, if we start our reasoning with this, can we go backwards? If we start our reasoning with this, then that means this. That means we can like split it into any two sums, assign one to B, assign one for D, and we can split it right. Okay, I guess it works then. Okay, I know why this works. Or maybe I don't. Never mind. So we have this, we have this. This is mod 1, right? 4 times 100. Since 9 divides 99. So we can in fact replace 400 with simply a 4. Again, we are appealing to our claim that we can replace the congruent elements, but we are really appealing to property 3 about the arithmetic of congruence. So 100 is mod 4. If we multiply both sides by 4, we multiply both sides by 4, then we get 400 congruent 4, right? I think it's easier if I start with this, yeah. 90 congruent 0 mod 9. We start with this. Then we add 400, we add 1, we add 300. That becomes this. Yeah, yeah, I understand now. I understand. Wanda. So this. So we add 3000 plus 400 plus 90 plus 1 congruent plus 9 plus 1. So what I'm doing is I'm adding this to both sides. Then I get this. And since this is congruent modulo x, because congruence is transitive. Yeah. Uh, and now we know that 100 modulo 1, right? If we multiply by 4, we get this mod 9. Then we get 1, 2, 3 plus 400 plus 1. 1, 2, 3 plus 4 plus 1 mod 9. Then we have x is 1, 2, 3 plus there. Now we know that 1000 is 1 mod 9. We know this. So therefore 3000 is 3 mod 9. Now 3000 plus 5 is 3 plus 5. Yeah, using the properties of congruence. We can add both sides by 5 using the properties of congruence. And then this is x 3 plus 5 mod 7. X is 7. Sorry, x is 8. Congruence to 8. The above example should convince you that the well-known divisibility test for 9 is true. Sum of the digits of a number is divisible by 9 if and only if the original number is divisible by 9. Find the remainder when 2 to the power of 123 is divided by 7. Find the number when 3 to the power of 123 is divided by 7. 6.24. Example 6.2.4. Find the remainder when 3 to the power of 123 is divided by 7. So 3 mod 3 mod 7. We know this is true. Hold on a minute. Hold on. Sorry. X. We know that um wait, let me think about this. Maybe should I choose 21? 3 times 7 is 21, right? What? Hold on. Nope. Maybe not this. Um, what about 3 cube? 3 times 3 is 9. 9 times 3 is 27. Uh, okay, we know this is true. So we multiply both sides by 3 to the power of 120. We get 3 to the power of, because we add the exponents. Yeah. Is 123 divisible by 3? It is, right? 41, I think. 41 times 3 is 123. So, wait. 3 to the power of 3 is congruent to 6. Don't we need to do this 41 times, maybe? That's what I'm thinking. Or maybe there is a better way. Of course, we are working with congruence because we want to find the smallest positive x such that x is congruent 3 to the power of 123. Now, first we write this. Or 3 to the power of 3 times 41. We have 27, 41, 641. Okay, so they raise both sides by 41. Wait, let me remove this. If I can multiply both sides, I can multiply the equation by itself 41 times. Since this Notice further that 6 square is 36 is congruent to 1 modulo 7. Thus, we can simplify further. 6 square is 36, which is 1 modulo 7. Uh, yes, 6 square modulo 1 mod 7 square raised by 20. 1 raised by 20 would be 1 modulo 7. That means 2 times 20 is 40 times both sides by 6 mod 7. And then, okay, so the answer is 6, right? In the above example, we are using the fact that if A is congruent to B, then A to the power of B is congruent to B to the power of B. This is just applying property 3 a bunch of times. So far, we have seen how to add, subtract, and multiply with congruences. What about division? There is a reason we have waited to discuss it. It turns out that we cannot simply divide. In other words, if A times T is equal to B times T, we do not know whether A is congruent to B mod N. Consider, for example, 18 congruent to 42 mod 8. This is true. Now 18 and 42 are both divisible by 6. However, this is not true. When this does not work, note that 3 is congruent to 7 mod 4. We cannot divide 8 by 6, but we can divide 8 by the greatest common factor of 8 and 6. Will this always happen? Suppose AD is congruent to BD mod N. In other words, we have AD is equal to BD plus KN for some integer K. Of course, AD is divisible by D, as is BD. So Kn must also be divisible by D. Now, if N and D have no common factors other than 1, then we must have D divided by K. But in general, if we try to divide Kn by D, we don't know that we will get an integer multiple of N. Some of the N might get divided as well. To be safe, let's just divide as much N as we can. Take the largest factor of both D and N and cancel that out from N. The rest of the factors of D will come from K. No problem. Call the largest factor of D and N the GCD of D and N for greatest common divisor. In our example above, GCD 6, 8 is equal to 2. Since the greatest common divisor of 6 and 8 is 2. I don't understand what they're doing here. We try to divide Kn, okay, Kn divided by D. We don't know if it will be an integer multiple. You'll get an integer multiple of N. Some of the N might get divided as well. To be safe, let's just divide as much of N as we can. Take the largest factor of both D and N and cancel that out from N. The rest of the factors of D will come from K. No problem. If D and N have no common factors, then GCD of D and is equal to 1. So A is congruent to B mod N. I don't understand what they mean by this, right? think I have a better proof over here. Divisibility, prime numbers. What is this? Congruence, right? Epsilon alpha is congruent to epsilon beta. If and only if alpha is congruent to beta, then GCD of this. Okay. Let's say congruent to CB mod M and let D be the GCD of C and M. So M divides CM minus CB, which implies M divides C times A minus B, which implies D is the greatest common divisor of C and M, right? So D divides M, D divides CB, so we can divide both sides by D. Since D is the GCD, then M divide, so the GCD of M divide D and C divide D is equal to 1. So we have M divides D divides A minus B, which implies A is congruent to B mod M divided by D. Hold on, because it gets built up from other proofs. So what we are trying to prove, not this, this. Since D is the GCD, then I think it's this one. If C divides AB and GCD of C and A is 1, then C divides B. Okay. Since GCD C is equal to 1, we have this. Since C divides BC and C divides AB, so C divides B. Okay. Since GCD of these two is 1, then this divides this. I need to add a link over here to this article. And we have A congruence B mod M divided by D. Therefore, CA congruent CB mod M implies A is congruent B mod M divided by D. As for the other way around, we have this. We multiply both sides by D. Then we multiply. I think if we have this, then we can multiply it with any integer, including C divided by D. And then we have M divides CM minus CB. Yeah, that was. I need to revise this. If D and N have no common factors, then GCD of D and N is equal to 1. So A is congruent to B mod N. Simplify the following congruences using division. AD BD mod N. But these two are not divisible by 5. Maybe we can add both sides by 1, right? Simplify the following congruences using division. You can add both sides by a 1 and then divide them by 5, right? Both 24 and 39 are divisible by 3. 3 and 5 have no common factors. Oh, GCD of 3 and 5 is 1. That makes sense. And this is mod 5. Yeah, that makes sense. Now that we have some algebraic rules to govern congruence relation, we can attempt to solve for an unknown in the incongruence. For example, is there a value of x that satisfies this? We just bring 2 to the other side, right? In this example, since the modulus is small, we could simply try every possible value for x. There are only there are really only 5 to consider, since any integer that satisfies the congruence could be replaced with any other integer that was congruent to modulo 5. Here, when x is equal to 4, we get 3x plus 2 is 14, which is indeed congruent to 4 modulo 5. This means that x is equal to 9 and x is equal to 14 and x is equal to 19 and so on will each be a solution because, as we saw above, replacing any number in a congruence with a congruent number does not change the truth of the congruence. Let's see how you could solve this using our rules for the algebra for congruence. Such an approach would be simpler than the trial and error. First, we know we can subtract 2, so 3x modulo 2. Next, we divide both sides by 3. First, we add 0 to both sides. Of course, on the right hand side, we want to add 0 to be a 10. We want that 0 to be a 10. This gives this. And then we divide both sides by 3. We have 4. Okay, example 6.2.6. 6.2.6. 7x modulo 12 mod 3. I should say congruent. 7x congruent. It's mod 13. 7x congruent 12 mod 13. And I have no clue. Hold on, let me see. 0 congruent 13 mod 13. But 12 plus 13 is 25. I don't think that gets us anywhere. What if I add 13 again? This is equal to 13. So if I add it with itself, multiplied by 2, 26 mod 13, what now? 26 plus 12 is 38. That doesn't send me anywhere. How about All we need to do here is divide both sides by 7. We add 13 to the right hand side repeatedly until we get a multiple of 7. So how many times did they add 13? 12, 13, 25, right? 13, 5, 3, 38. 30. How many 13s are we adding? 8, 3, 1, 3, 1, 1. Oh my god. 6, 4. This is the last 13. 1, 7. So 1, 2, 3, 4, 5. I don't think that mattered. So at 7. So we times it by 5, right? No, no, no. We got this wrong. At 12. 12 plus 13, 5. 7x modulo this. 77 mod 13. Divide both sides by 7. Since GCD is 1, we get this. This is 1. Time for 2. 84x minus 38. 79 mod 15. Nine, 8, 17. 7, 3, 10, 1, 1. Now let me think about this. 3 times 20 is 60, right? 3 times 30 is 90. Minus 3 is 84. 3 times 10. 3 times 30. 3 times 30 is 90. Minus 3. 84. 29, 28. 28. What about 117? 3 times 40. 3 times 40 is 120. 3 times we go one number back. 39 is 117. 39 mod 15. Whoops. No, no, yeah, it's correct. Hold on, I can divide it by 3 for the right. No, I can't. 15 divided by the GCD of 3. 15, which is 3. 15 divided by 3 is 5. I have no clue. Should we make this a multiple of 20? No, wait a minute. Um, huh. I was thinking of taking 28 out. No, wait, we can simplify 39, right? 1 mod 5. 1 mod 5. This is the answer, right? Um, no, it's negative 1. Or I can just write 4. We can divide both sides by 2 and 2 again. Am I doing this right? Divided by 4 and 2 and 5. It doesn't change. We have 84. Zero is, that looks like a heart. 0 is 25. 25, which is mod. I can plus it with itself, so times 2. So another multiple of 5 is 10. plus 1, 11. 15 plus 1, 16. 20 plus, okay, 20 should work, right? So 7x is equal to, add this plus 1. So 1 mod 21. Yeah, 21 is congruent to 1 mod 5. Yeah. X 3 mod 5. They said 8. Wait, 8 and 3 works. So the solution are those values that are congruent to 8 or equivalently 3 modulo 5. Yeah. What is 20x 23 mod 15? 23 mod 15. So we have so 20 is modulo 7 mod 15 and 23 7. No, wait a minute. 6 is this is 6. 6 plus 3 is 9. So I should write it here. This implies 20x modulo 6x. This implies, this doesn't imply. Then we have 26, 23. Instead of 6x, 20x, I can write 6x. Instead of 23, I can write. Yeah. If we divide both sides by 3, I get 2x modulo 3 mod GCD of 14 and 13. It's 1, right? They're a co-prime. 1. Yeah, they're a co-prime. So it's just 14. Now we have this. Now do we check it manually? So what number is modulo 3, 14? So 14, 17, right? So we have 3. Then we add 14, 17. Then we add 14 again. No, but that wouldn't work because 3 is odd. We keep adding an even number, we will get odd. Would this even work? We have to find some multiple such that 3 minus 2, some value of 2x such that 2x minus 3 gives 14, or any multiple of this gives 14. Like 2x minus 3 is a multiple of 14. But 3 is odd. Even minus odd would give odd. Wait. Oh, thus there are no solutions to the congruence. The last congruence above the way in which congruences might not have solutions. Could have seen this immediately. In fact, look at the original congruence. We write this as an equation, we get this, or equivalently this. We can easily see that there will be no solutions to this equation in integers. The left hand side will always be even, but the right hand side is odd. Similar problem would occur if the right hand side was divisible by any number, then the left hand side was not. So in general, given the congruence AX congruent B, if A and N are divisible by a number by which B is not divisible, then there will be no solution. In fact, we really only need to check one divisor of A and N, the greatest common factor. Thus, a more compact way of saying to say this is GCD AN not divisible by B, then AX is congruent to B has no solution. If A and N are divisible by a number by which B is not divisible, then there will be no solution. If A and N are divisible by a number, okay, so we can using this, we can write this. If 20 and 14 have a divisor which does not divide 23, then there'll be no solution for X. But why do we only check GCD? I mean, it would work for any divisor, right? But GCD would be like the best guess. So if there's any divisor that divides this, but not this, then these two cannot be equal. How much is left? Okay. Solving linear how do you pronounce this? Uh, Diophantin equation. Discrete math deals with a whole number of things. So when we want to solve equations, we usually are looking for integer solutions. Equations that are intended to only have integer solutions were studied by the 3rd century by the Greek mathematicians Diophantus of Alexandria. As such, are called Diophantin equations. Probably the most famous examples of a Diophantin equation is a square plus b square equals c square. The integer solutions to this equation are called Pythagorean triples. In general, solving Diophantin equations is hard. In fact, probable there's probably no general algorithm for deciding whether a Diophantin equation has a solution. A result known as Mathias-Sebeck theorem. We restrict our focus to linear Diophantin equation, which are considered easy to work with. An equation in two or more variables is called a Diophantin equation if only integer solutions are of interest. A linear Diophantin equation takes the form a1 x1 a2 x2 and x1 is equal to b for constants a1 all the way to an and b. A solution to the Diophantin equation is a solution to the equation consisting only of integers. Here are the tools we need to solve linear Diophantin equations. We will consider as a main example the equation 51x plus 87y is equal to 123. The general strategy will be to convert the equation to a congruence and then solve that congruence. First, check if perhaps there is no solution because the divisor of 51 and 87 is not a divisor of 123. Really, we just need to check whether GCD 5187 divides 123. This greatest common divisor is 3 and as 3 divides 123. Hold on, but what if GCD divides them, but there is some other divisor that doesn't divide them? At this point, we might as well work out, we might as well factor out this greatest common divisor. So instead, we will solve 17x plus 29y is equal to 41. We divide both sides by 3. Now observe that if there are going to be solutions, then for those values of x and y, the two sides of the equation must have the same remainder as each other, no matter what we divide by. In particular, if we divide both sides by 17, we must get the same remainder. Thus, we can safely write okay. If the two sides are equal, then they should give the same remainder. We chose 17 because 17x will have remainder 0. This will allow us to reduce the congruence to just one variable. We could have also moved to a congruence modulo 29, although there is usually a good reason to select a smaller choice. This will allow us to reduce other coefficient. In our case, we reduce congruence as follows. 17x 41. We reduce it to 0. Okay, we get rid of 17x. 29y congruent 41. Why is it 12 and 7? Why did they do this 12 by congruent 7? Why is congruent 2? Okay, this I understand. I don't understand what's going on. 41. Now at this point, we know y is equal to 2 plus 17k. Now, will work for any integer k. If we haven't made a mistake, we should be able to plug this back into our original equation and get x is equal to minus 1 minus 29k. Also found all solution for the Diophantine equation for each k satisfy the equation. Could check this for a few cases. K is equal to 0, the solution is minus 1, 2. And yes, we get this. This works. K is equal to 3, we get minus 8853. If k is equal to 2, 5732 minus 32. Wait, 29 minus 17. Okay, that makes sense. 29 is modulo 17. Sorry, 29 is modulo 12. 41 is modulo 7, right? Okay, I think I understand. To summarize this process, solve ax plus by equals c. Divide both sides by the equation by GCD. If this does not leave the right hand side as an integer, there are no solutions. Can you make 6.37 using just 5-cent and 8-cent stamps? What is the smallest and largest number of stamps you could use? They're asking us if we could use some 5 cents and some number of 8 cents. $637 is 6.37 cents, right? Yeah, yeah. Now this is 2. Then we have, let's do 5x plus 8y modulo, wait, 673 modulo 5. The GCD of 5 and 8 is 1. Then we can remove this. We have 6, 3, 7. 6, 3, 5 is a multiple of 5, right? Then I guess 2 over here. 6, 3, 7 modulo 2. And then 8 modulo 8 modulo 3. 8y becomes 3y. 67 becomes 2. Now the question is, so y could be 2, right? So some multiple of 5 given by 3y minus 2, some multiple of 5 plus 2 divided by 3. 3y minus 2. Is this even correct? Uh, yeah, so y is congruent to 2. Therefore, this. And then we have, and then we have this. Again, write that in our original equation. Some multiple of 637. 637. No, 637 is equal to 5x plus 8y. Five x plus a5 plus 2. What about x though? Should we do this again but mod 8? They got 4. 2. Oh yeah, 6 could be. No, if y is 2, 3 times 2 is 6, but that's modulo 1. Hold on a minute. Yeah, I got this wrong. 3 to 12. Okay. Yes, I got this wrong. 3 times 4 is 12. But this equation should work for any k, right? Or not? Y is equal to 4 plus 5k. Okay. 5x, this plus 5k is equal to 634. I forgot the 8 times. 4. Forty, 40k. Is this correct? Minus 32 minus 40k equals x. Yeah, I have to divide the entire thing by 5. 605 minus 40k. 120. I don't know if this is correct though. 121. So then we have 636, 637. 521 minus 8k. Instead of 8y, I'm going to write 40k plus 32. No, I don't need to write that. I just need to find values of x and y, right? So when k is equal to 1, k is equal to 2. So the largest possible is 125. What is the smallest and largest number of stamps you could use? As few as 80. K is equal to 15. We have x is equal to 1. And 80 stamps or as many as 125 stamps. Using this method, as long as you can solve linear congruences in one variable, you can solve linear Dipotine equations of two variables. There are times, though, that solving linear congruences is a lot of work. For example, suppose you need to solve 13x congruent 6. You could keep adding 51 to the right hand side until you get a multiple of 13. You would get 57, 108, 159, 210, so on. It's the first of these that is divisible by 30. This work is really too much work. Instead, we could convert back to a 17 equation. 13x plus 6 plus 51k. Now solve this like we have in this section. Write it as a congruence modulo 13. This and k is equal to 6. K is equal to 6 plus 13j. I'll go back and figure out x. X is 24 plus 51j. Of course, you could do this switching back and forth between congruences and Diophantine equation as many times as you like. Only use If you only use this technique, you can essentially replicate the Euclidean algorithm, a more standard way to solve Diophantine equation. Right, looks like I'm done with this book. I'll keep coming back to these topics in the future, but looks like this is the end of this book. All right, I will end my stream here. And yeah, see you guys next time. Bye.